Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD scholar, IIT Palakkad. This is the week 5 of the live discussion section of the course Turbulent Combustion Theory and Modeling. In this week, we will discuss the lectures number 21 to lecture number 25 by Professor Ashok De Sir of IIT Kanpur. In this section, we will discuss some of the problems related to these lectures, which will be helpful in solving your assignment problems and also understanding the concepts. In this section, all the problems are taken from the book An Introduction to Combustion Concept and Application, 3rd edition, 2017, McGrail. Okay, all the questions are taken from this book. This live discussion 5. Now let's come to our first question. Here 9.7 means chapter 9 and question number 7. You can refer to the book as I discussed above. From the definition of mixture fraction F, show that equation 9.44a is correct. Okay, what is 9.44a? That I will show. Okay, and we will show that this equation is correct or not. Okay, according to the definition of mixture fraction F. Okay. Okay. Now let's see what are the things given. Definition of mixture fraction F. Okay. To show equation 9.44a is correct. Okay. Now let's go to the solution part. Here the equation 9.44a is YF is equal to F minus F stoichiometric divided by 1 minus F stoichiometric. Okay. Okay, where this formula, this is the 9.44a. You can refer to book also for this formula. Okay, now when this formula is applicable, okay, for a particular condition, when f of stoichiometric, that is mixture fraction of stoichiometric, is in between, sorry, f of stoichiometric is less than f. F means any f, okay, maybe f actual, okay, is it also less than n. Okay, what does it mean? Okay, when this condition is there, okay, this condition is there inside the flame. Okay, okay, what is this yf? Yf is our what? Mass fraction. Okay, okay, now this is the relation between the mass fraction of the f means fuel. Okay, f means, can write down in different ink. F is equal to our fuel. Okay, since we know what is the definition of f, so we can write down f is equal to yf plus 1 by nu plus 1 yf product, where fs or f of stoichiometric is equal to 1 by nu plus 1. Okay, where this nu, all this thing came into existence, I just write down, let it be 1 kg of fuel plus nu kg of oxidizer gives rise to 1 plus nu kg of product. Okay, we know since summation of yi is equal to 1 y of product is equal to 1 minus y of fuel. Okay, now we can solve the above expression. Okay, or by substituting these values in the above equation of f, mixture fraction. Okay, f is equal to yf plus fs into 1 minus yf. Now rearranging, f is equal to yf into 1 minus Fs plus Fs. Okay. Now what is YF? YF is equal to F minus Fs divided by 1 minus Fs. Hence proved. Okay. Now let's move on to our next question. A circular port and a square port burner operate with the same mean velocity and produce the same flame length. What is the ratio of the circular port diameter capital D to the length of a side B of the square port? The fuel is methane. Okay. Now for this question, we will see what are the things given. A circular and a square port burner both operating at the same mean velocity and producing the same flame length. To find ratio of the just a second. To find the ratio of the circular port diameter to the length of a side if the fuel is methane. Okay. Now what are the assumptions? Roper's correlation apply. T infinity and Tf are the same in both cases. Okay. Solution. Circular port. First case is circular port. Then we just go for the square port. Okay. For the circular port, QF is equal to VE pi into D square by 4. LF is equal to 1330 QF T infinity by TF. Ln of 1 plus 1 by S. What is S? That I will tell. Actually, it's very simple. S is our 4.76 times A. Okay. And what is A? A is equal to x plus y by 4. We already discussed all these things. Okay. Now we just stop with this LF. Then we go for the square port. And finally, we just take the ratio of it by putting the all the values. This is our plan. Okay. Now this is for circular port. Let's go for our square port now. Now for square port, QF is equal to BE into B square. BE is the exit velocity and B is the length of a side. Of square. Now the laminar flame length is, we know the formula, 1045 into QF T infinity by TF. Now here you see here LF is equal to 1045 T infinity by TF. Okay. Divided by inverse F of 1 plus S to the power minus 0.5 whole square. Okay, by now substituting the value of QF. Okay, now laminar flame speed reduces to LF is equal to 1045 VE B square T infinity by TF divided by inverse of F 1 plus S to the power minus 0.5, then whole square. This is the flame length for the square port. And we just already calculated the flame length for the circular port. Now setting two flame lengths as equal, okay. Now you have to just equate the circular port and the square port flame lengths. Okay. One three three zero VE divided by 4 pi d square T infinity by TF divided by ln 1 plus 1 by S is equal to 1045 VE B square T infinity minus TF divided by INBR of F. These all INBR of all these things calculated from the error function. Now by solving all these things, we just get the ratio of diameter to the one of the length of the square port as 1.004 ln 1 plus 1 by S divided by inverse of F 1 plus S to the power minus 0.5 square. S is equal to 4.76 times A. 4.76 times x plus y by 4. Okay. What is the fuel here? The fuel is methane. Okay. CH4. What is the x? 1. What is the y? 4. 1 plus 4 by 4 is what? 2. 4.76 into 2 is equal to 9.52. Okay. We get the value of S as 9.52. Now substitute in this equation, above equation. D by V is equal to 1.004 ln 1.105 divided by inverse F 0.308 square. Okay. Now this I and V are of 0.308, where these values are there in some table in the book. Okay, that I want to mention. Okay, you just check table 9.4 page 338 of our prescribed book. I already mentioned the book name, everything. An Introduction to Combustion, 3rd edition, McGrill by S.R. Tunn. Author name is S.R. Tunn. Okay. Now, when you go to this table 9.4 at page 3.3 page 338, you see the inverse F, or we can write down it as INV of error function of omega. Let it be some value omega. Okay, that is equal to 0.28. Okay, and what is this value of omega? Omega is our this value. Okay, 0.308. Okay, so when you calculate, the values comes out to be 0.28 of this inverse of F of 0.308. Okay. Now this D by B value comes out to be 1.13, and this is the answer. Now let's move to our next question. Two circular port burner have the same mean velocity VE, but the velocity profile of one burner is uniform, whereas the other has a parabolic distribution. V of R 2 VE 1 minus R by R square. Determine the ratio of the momentum flow of the two burners. Okay, this is the question. Let's see what are the things given. Two circular port burner with the same mean velocity VE, but different velocity profiles. Okay, so now here there is two cases are there. Okay, one is the top hat profile and another one is your parabolic profile. Okay, how I know one case is top hat? Because here you can see two circular port burners with the same mean velocity VE. What does it mean? It means that this case is same as your top hat profile. Okay, okay, this is the condition for the top hat profile. Okay, from there I understand this is the top hat profile case. Okay, and other parabolic case anyway it's already given. This is the parabolic distribution already given. Okay, case 1, top hat profiles BE is equal to BE bar. Case 2, parabolic profile B of R is equal to 2 VE bar 1 minus R square by capital R square. To find ratio of the momentum flows for the two burners. Now, what are the assumptions? Constant properties. Burners have the same diameter ports. Solution: Je is equal to momentum flow is equal to m dot of v, and we know that what is m dot is equal to rho v times a. For case 1, JF1 is equal to rho VE A into VE, which gives rise to rho VE into pi r square. For case 2, J2 is equal to 0 to r rho times 2 BE bar 1 minus r square by capital R square 2 pi r into dr. Now let's do the integration. Just take the constant outside. Substitution. Let's do some substitution. Du is equal to minus 2r into dr. At r equal to 0, u is equal to capital R square. At r small r is equal to capital R, u is equal to 0. Okay, I I just only substitute in this equation u is equal to capital R square minus small r square. Okay, now we have to just change the limits and change the integrating constants. Integrating variable we just have to change. Okay. Now the equation reduces to 4 pi rho VE square divided by r to the power 4 r square to 0 u square minus of du. Okay, is equal to 4 pi rho VE square divided by r to the power 4th. Okay, just change the limits 0 to r square and multiply by the negative sign -1, which gives rise to u square into du. Now just do the integration. Four pi rho be bar square divided by 3r to the power 4th u cube 0 to r square 4 pi rho be bar square 3 r to the power 4 r square cube minus 0. So finally the values of J2 comes out to be 4 by 3 rho VE bar square pi r square. Okay, now we have the value of, where is it, JE1. Okay, we have the value of JE1 and we now also get the values of what, JE2. Okay, now just to take the ratio. JE2 by JE1 is equal to 4 by 3 rho BE square pi r square divided by rho BE square pi r square. All thing will cancel and the values comes out to be 4 by 3. So our answer is 4 by 3. Okay. Now let's move to the next question. Now in this question, let's read the question. In determining the constant associated with the experimental flame length for a correlation in 9.60, Roper used a flame temperature of 1500 Kelvin. What value of the mean diffusion coefficient D infinity appearing in the equation 9.59 is consistent with the constant in equation 9.60. How does these values compare with the value of binary diffusivity for oxygen in air at 298 Kelvin and D of O2 and air is given as 2.1 into 10 to the power minus 5 meter square per second. Here we need to find out the value of D infinity, okay, and we have to compare with the value of DO2 and air, okay. Is it same or is greater than or less than or whatever, we have to just check it, okay. Let's see what are the things given. Given is Roper's experimental flame length correlation with a flame temperature of 1500 Kelvin. Now let's see what is equation 9.66a 9.60, sorry. Flame length experimental is equal to 1330 UF into T infinity by T F divided by ln of 1 plus 1 by S, okay. To find mean diffusion coefficient D infinity appearing in the theoretical flame length equation 9.59. that is consistent with the constant in equation 9.60. Now, what is 9.59? Let's see. LF theoretical is equal to QF T infinity by TF divided by 4 pi D infinity ln of 1 plus 1 by S T infinity by TF to the power 0.67. Okay. This is LF theoretical. Okay. Now you see what are the assumptions. Assumptions T infinity equal to 300 Kelvin. Okay. Now second assumption is experimental and theoretical flame lengths are equal. And let's come to the solution part. LF theoretical is equal to LF experimental. This is already given in the question. Okay. Just we have to equate these two values and find out the value of D infinity from this. That is the only task we have to do. QF T infinity by TF divided by 4 pi D infinity ln of 1 plus 1 by S into T infinity by TF 0. To the power 0.67 is equal to 1330 QF T infinity by TF ln 1 plus 1 by S. Now what are the things we can cancel? We just check QF we can cancel, T infinity by TF we can cancel, ln 1 plus 1 by S ln 1 plus 1 by S cancelled. Now the expression of d infinity comes out to be d infinity equal to 1 by 4 pi 1330 into t infinity by tf to the power 0.67. Okay, this is the expression for diffusivity at the infinity or at the surrounding, whatever you can tell. Okay, or at the ambient. Okay, now just substitute the values of t infinity and tf. Now this value comes out to be 2.035 into 10 to the power minus 5 meter square per second, which is equivalent to d of O2 air, which is equal to 2.1 10 to the power minus 5 meter square per second. And we can see here is that this is nearly same value. You can give the comment that nearly same values. Okay, this is the comment we can make. This is not required. Okay, okay, now let's move on to the next question. Now in this question, estimate the Lewis and Schimm's number of for a dilute mixture of O2 in air at 298 Kelvin and 1 atm. Assume d of O2 air is equal to 2.1 10 to the power minus 5 meter square per second. At these conditions, discuss the implication of your result. Okay, now what are the things given? Dilute mixture of O2 in air. Just a second. In air at 298 Kelvin and 1 atmospheric. To find Lewis and schemed numbers. Assumptions d of O2 air, that is diffusivity, equal to 2.1 into 10 to the power minus 5 meter square per second. Alpha and nu are same with a dilute mixture of O2 in air at 298 Kelvin. Alpha of air is equal to 22.5 10 to the power minus 6 meter square per second, and nu of air is equal to 15.89 10 to the power minus 6 meter square per second. Where I get these values? I get all these values from appendix C.1. Okay, of the book Introduction to Combustion, 3rd edition by a certain author. You can take these values for air. Okay, now what is the formula for Lewis number? Alpha by D. 22.5 into 10 to the power minus 6 divided by 21 into 10 to the power minus 6. So Lewis number gives rise to be 1.07. Now Schem's number, what is the formula? Nu by D, and for values are 15.89 into 10 to the power minus 6 divided by 21 into 10 to the power minus 6. What is the values comes out to be? The values comes out to be 0.757. Okay. Okay, now we can write down the notes, because in the question it asks that discuss the implication of the your result. Okay, so we just write down one note to signify that answer of that question. For the given air properties, L equal to 1 is a reasonable assumption. Whereas SC is equal to 1 is not quite good for research related problems, because the values comes out to be 0.757. Okay, and there is a high amount of error is there. Okay, okay. Now let's come to the next question. A temperature sensor is to be placed above a methane air jet flame along the extension of the flame's center line. It is desired to locate the sensor as close as possible to the flame. However, maximum temperature operating limit of the sensor is 1200 Kelvin. The system operates at 1 atm and the air and fuel enters at 300 Kelvin. Using the simplified state relationship for a diffusion flame, determine the mixture fraction that would correspond to a sensor temperature limit of 1200 Kelvin. Assume a constant specific heat Cp of 1087 joule per kg Kelvin. Using the constant density laminar jet equation, determine the axial distance along the center line from the burner nozzle exit to the sensor location corresponding to the conditions in part A for a non-reacting jet. Use a jet Reynolds number rho EVE R divided by mu. This is the normal formula we know of 30 and jet radius capital R of 1 mm. Okay. So now this question is looking very big, but this question is very simple. Okay. As I proceed further. Now let's see what are the things given. Pressure is equal to 1 atmospheric. Tf is equal to T air is equal to 300 Kelvin. Cp is equal to 1087 joule per kg Kelvin. T flame max is equal to 1200 Kelvin. Reynolds number of jet, RE of jet 30. Jet radius okay. Now let's see what are the things to find. A mixture fraction F at 1200 Kelvin. B axial distance along the center line let it be value x. Okay, these are the two things we need to find out: mixture fraction F and the axial distance along the center line x. Let's see what are the assumptions. Okay, here we just assume one assumption, that is simplified state analysis or a simplified state relationship. Now if you are finding the mixture fraction, okay, at 1200 Kelvin, okay, so this is and this is the maximum flame temperature, okay. So from this we understand that this is not in this is at the outside of the flame sheet, okay. So you have to think this these are the tricky part of any of the problem. So you have to think carefully. For this case, this is we know from this given values we understand that okay, this is the outside of the flame sheet. Then we have to use the formula for the outside the flame sheet, the temperature formulas for outside the flame sheets and other formulas, then to proceed further. This is the trick behind these all these questions, okay. Somewhere some question it should be inside the flame sheet also, okay. So you have to think carefully and then proceed further in this question, otherwise everything in this question will be wrong, okay. Because here I understand from this question this is the outside the flame sheet, so I will accordingly proceed further in this question. It is the case of outside the flame sheet. And what is the condition for outside the flame sheet? And for this thing we have to use the equation 9.5. I will write down the equation next thing, next page. Now here you have to use the equation outside the flame sheet means you have to use the equation 9.51c from the book, okay. Next page I will write down the equation directly, okay. T is equal to T of F is equal to function of delta SC divided by Cp plus T of fuel exit temperature minus T of oxidizer at infinite or at ambient, whatever, plus T of oxidizer at infinite, okay. This is equation number 9.51c. Now what is delta HC? Okay, delta HC, heat of combustion, we can take either lower heating value or we can take either higher heating value, okay, for the methane. But here we take the lower heating value of methane, okay, from appendix B. So why we just taken, because here one condition is there, we just assuming that okay, for lower heating value none of water assumed to condense, okay. This is the condition for lower heating value, okay. That's the reason why we taken, okay. Now here we just directly find out the value of mixture fraction F. F is equal to, just rearranging the previous equation, we get as now here Tf infinity and T oxidizer infinity as is equal to, we just cancel it out because is given that Tf infinity is equal to T of oxidizer infinite is equal to 300 Kelvin given. Okay. Now substitute the values and get the answer. The values comes out to be 0.0196. Okay, and this expression having no unit. Okay, no unit and no dimension, mixture fraction. Okay, because Kelvin divided by kilojoule per kg divided by kilojoule per Kelvin gives rise to be what? There is no unit. Okay, all are cancelled. Okay, if you see the units. Now let's go to the next bit. B bit. Here we just have to calculate the axial distance along the center line. Okay, so using constant density jet solution, what is this equation? Equation 9.18. It's already given in the book. Okay, now we have to just substitute this equation. Okay, YFO is equal to 0.375 Rij x by r to the power minus 1. Now for a non-reacting jet, okay, for a non-reacting jet, Y F of O is equal to mixture fraction. Okay, now this formula, above formula reduces to x is equal to 0.375 Rij of R divided by F. Okay, now let's substitute the values. X is equal to 0.375 into 30 into 0.001 divided by 0.0196. And this value comes out to be 0.574 meter. Now, now in this question, now we just solve all the mostly all the questions of chapter 9. Okay. Now we will solve two problems from the chapter detonation. Okay, which is chapter 16. Okay. Now let's see first question of detonation, 16.2. Determine the velocity of a detonation wave propagating through an ideal gas mixture having a constant specific heat Cp of 1200 joule per kg Kelvin. The mixture is initially at 2 atmospheric and 500 Kelvin. The heat release per unit mass of mixture is 3 into 10 to the power 6 joule per kg, and the mixture molecular weight is 29 kg per kilomole. Okay, this is the question given. Okay, now we just see what are the things given. Given. Okay, now we see what are the things given. Given is detonation wave propagating through ideal gas mixture. Cp given as 1200 joule per kg Kelvin. Pi 2 atm. Ti 500 Kelvin. Q of mixture is equal to 3 into 10 to the power 6 joule per kg. Q of mixture is heat release per unit mass. Now molecular weight of the mixture is also given, which is 29 kg per kilo mole. To find VD, velocity of detonation, assume constant Cp is second is molecular weight, third is P2 is very greater than P1. Now what does this P2 is very greater than P1 means? It means that pressure of unbound gases is much greater than that of the unbound mixture. Okay. Now let's go to the solution. Detonation velocity Vd equation 16.27. Vd is equal to 2 into gamma plus 1 into gamma r T1 plus Q of mixture divided by Cp. This is the formula of the detonation velocity. Where R is equal to Ru divided by molecular weight is equal to 8315 divided by 29 is equal to 286.7 joule per kg Kelvin. Gamma is equal to Cp by Cv is equal to Cp divided by Cp minus R. Okay, so Cp minus Cv is equal to R. We already know. So the values comes out to be 1200 divided by 1200 minus 286.7. Gamma is equal to 1.314. Now by substituting all the values in the equation of Vd, detonation velocity, by substituting all the values we get Okay, by solving all these equation, we get the values of Vd as 2287 meter per second. Now here sometimes it may ask about the units. Okay, so I just also show you the how this unit of meter per second came into existence. Okay, here joule per kg Kelvin into joule per kg divided by joule per kg Kelvin to the power 1 by 2 joule per kg Kelvin into Kelvin. Kelvin get cancelled. Newton meter divided by kg to the power 1 by 2 or kg meter per second square into meter divided by kg. Now the value comes out to be meter per second, which is the unit of what? Vd. Okay. Now let's proceed to our next question. Prerequisite is Z and D. What is Z and D? Here Z and D written. So what is this Z and D? Okay. Zeldo which. Okay, I just read the question again. Assuming the Z and D structure, determine the key state properties for the detonation wave described in problem 16.2. That is the previous question. That is, calculate rho, p, t and Mach number at state 1, 2 dash and 2. What is this 1, 2 dash 2, everything, and now I just write down in this prerequisite part. Okay. Z and D means Zeldovich and von Neumann and Doring model or shock structure. States. States 1 is upstream condition. Two dash is condition at the end of the leading shock. or shock front. Now what is 2? 2 is Chapman Jognet point or end of the combustion. Okay. Now what are the things given? Distonation wave of problem 16.2. P1 is equal to 2 atmospheric. T1 is equal to 500 Kelvin. To find rho P T Mach number are the at states of 1, 2 dash and 2. Assumption. Assume Z and D structure model. Let's start the solution. State 1. P1 is equal to 2 atm. T1 500 Kelvin. These are the things given. Rho 1 P1 by R T1 101,325 divided by 286.7 into 500. What is rho 1? 1.414 kg per meter cube. Okay. Now what is Mach number? 1. Detonation velocity divided by gamma R T1 to the power 1 by 2. That is 2287 divided by 1.314, 286.7 and into 500. Into 1 by to the power 1 by 2. This value comes out to be 5.27. That 2 dash P2 dash is equal to P1 1 by gamma plus 1 2 gamma ma1 square minus sorry, this is gamma minus 1. Okay, this is the formula for P2 dash. Just substitute the values. One atm is equal to 0.101325 megapascal. Okay, now P2 dash is equal to 62.2 atm is equal to 6.363 megapascal. Similarly, T2 dash is equal to T1 2 plus gamma minus 1 into Mach number 1 square 2 gamma ma1 square minus gamma minus 1 divided by gamma plus 1 square ma1 square. Five hundred 2 plus 0.314 5.27 square T2 dash 2620 Kelvin. Okay, rho 2 dash by Delcase equation directly you can find out the value as 8.47 kg per meter cube. Now what is the Mach number? Let's say 2 dash. B2 dash by C2 dash. One point 414, 8.47, 2287, 1.314, 286.7 and 2620. Okay, to the power 1 by 2. Okay, what is this Mach number 2? 0.38. Okay, now let's proceed to the state 2. T2 is equal to 2 gamma square divided by gamma plus 1, T1 plus Q of mixture divided by Cp. Okay, what is this value now? 2 into 1.314 square, 2.314, 500 plus 3 into 10 to the power 6 divided by 1200. Now the T2 values comes out to be 4477 Kelvin. Now rho 2 is equal to rho 1 gamma plus 1 divided by gamma. 1.414, 2.314 divided by 1.314. Gamma 2 is equal to 2.48 kg per meter cube. Okay. Now applying the ideal gas equation. Apply ideal gas equation of state to find P2. P2 is equal to rho 2 R T2 is equal to 2.48, 286.7 into 4477. Then the value of P2 comes out to be 3.183 megapascal. Now what is the value of Mach number 2? V2 by C2 rho 1 by rho 2 into V1 divided by gamma R T2 to the power 1 by 2. 0.568 2287 divided by 1.314 286.7 4477. Okay, to the power 1 by 2. The value of Mach number 2 comes out to be 1, and it is also as expected. Okay, why I am telling as expected? Because at the end state it will be 1. Mach number is equal to 1 of the detonation. So our calculations are correct. Now we can just summarize all the results at one place. Rho P T Mach number at state 1, 2 dash and 2 and the units. Okay. Okay. One point 41, 8.47, 2.48 kg per meter cube. 0.203, 6.363, 3.183 megapascal. 500, 2620, 4477 Kelvin. Mach number 5.27, 0.38 and 1. Okay. Okay. This is the summary of the results. Now we can end the section. You should go through all the question again and try to solve it again, all these questions. and go through the lectures carefully from 21 to 25. Okay, if there is any doubt, you can ask me in my YouTube channel. Sumit Sagar Hota is the channel name, and also you can ask in the questions in question and answer forum in NPTEL. Okay, and try to attend the section also. Okay, thank you very much for attending the section, and if you are also watching the recorded, thank you very much in YouTube.